So I guess the first question I have for people is, what proportion of you have taken 212? Raise your hand, just curious. It's about half. Who took it over the last couple of quarters with Sarah? And then who took it earlier than that with either Stu or me? So interesting. I used this slide deck in that class, and I'm actually not sure if Sarah did. I shared all of my materials that I had historically used, so maybe this will be something that you have seen before. Does anyone recognize the very beginning of this as something that they've seen? I feel like UML is a very important thing to know going into software engineering, especially when you're making a UML editor. So it's worth the refresher probably. I don't intend to spend a long time on this because we need to get into how to develop the actual processes of development. But we're going to start just talking about UML very briefly. So the room mic is working. Are people still able to hear me on Zoom? That's not weird. It's just a visual, it's just an audio bug. It's telling me that the speaker is not detected, but it's working.
I know that Wayland has an issue with rendering on like Simply Data.
Yeah.
If you switch back to Tor, it gets recorded.
I know.
Now my mouse is where are you? Second screen. All right. My laptop has left the meeting. How about now? Still reverb? Perfect. Okay, so I didn't need to do anything at all.
It's not in sports and concert. Just roll. So
And we're off. All right, so perfect. Sorry for everything. We'll get through this quickly though. So UML is a way to model the internal representation of a program. So you're describing the actual system at a high level. This is very useful if you are communicating with either people who are non-technical or people who are on your team and don't necessarily want to speak about it technically. It's a nice overarching visual way of representing a complex problem in a very easily digestible way. So some history that we don't really need probably. Stands for Unified Modeling Language, great. Even though it says unified, it was designed by a committee and there are lots of different approaches to UML. So I'll briefly go over some of the different approaches to how to design a visual representation of your project. And that will give you a way to get a sense of how to do that within your groups. Because I think especially during the design phase of your sprints, it's very useful to all leave on the same page, and you don't want a long technical document of everything that you discussed. You want to have a small, easily digestible visual image that you can turn into the technical requirements, but it's a nice starting point for visualizing what's going on. So we'll talk about all of these different diagram types very briefly, because again, I don't think this needs to be quite as in-depth as this entire slide deck is, and then we'll move on. First one, a use case diagram. We just really need to see who is using the system. So we have actors within the system. We have use cases. So what are they using the system for? And then we have relations. How are the pieces of this connected? As an example, probably have seen this example if you've seen this slide deck. This is a restaurant system. The actors in this are the waiter, the client, and the cashier. Those are the users of this system. there's a system boundary there that there are people and there are people who use the system. So the system is embedded within that internal rectangle. There's also the chef, I guess, and you can see him hiding there on the right, him or her. There are classes and objects within that handle things like the ordering of food, the serving of food. When do all of these things happen? But you can now see a fairly small representation of what this system looks like from the outside. It's a complex system with lots of interworking and interrelated parts, but this gives you a visual way of breaking that down, determining who is responsible for what, in what order or when, and how are these objects related to each other? Yeah.
Is a swim lane diagram like an example of a use case diagram, or is that like something completely different?
Sorry?
Swim lane, where like you have basically like actors in the swim lanes,
Yeah.
the process.
Yeah, so that is reasonably similar to that, depending on the actual use for it. So the use for a use case diagram is just, it's who's using the system for what purpose and how are they related to each other? How are the components related to each other? If a diagram does that, it is a version of a use case diagram. If the purpose is something else, then it's one of these other diagram types. Or something different from that. So another example, you can make this as vague as possible, really, and more specific in different diagrams. So you don't have to cram everything onto the same diagram. You can use different levels of a hierarchy, I guess, of this. So in words, something very simple would just be something like, all right, a resource manager manages resources, project manager manages projects, etc. Looking at a visual representation of this, it's not that complicated. So you can put it on a very high level. The user is the resource manager. What is the task that they do? What is the part of the use case they do? They manage the resources. Great. All of those words are now embedded into this very simple diagram that doesn't tell you a ton. But we can make this more complicated because manage resources is an incredibly vague term. What does that entail? What are all of the components of managing resources? This can be the high level diagram, and now we can zoom in on different components of this and show the use case of, all right, how exactly is this done and interacted with? So a project manager can add, remove, and update a project. Removing and updating projects need you to find the associated project, etc. So here is an example of, now we've blown up managing projects. And there's only one user, the project manager. But now we can actually see how that one bubble on the last two slides ago, actually works internally without trying to shove all of this onto that diagram within the context of the system at large. Question?
So the use case diagram is like basically like bare bones representation of how the program works.
Yeah.
So it's not like.
There's no detail, there's no code, we don't even necessarily know how each of these classes break down. What are their fields? What are their methods? It's just, what is the purpose?
This particular diagram, this isn't really a use case diagram though, right? Because you wouldn't really use that if there was only one actor.
Potentially.
Okay.
This would show how this user interacts with this system in what ways. So yes, technically, I believe I would say that it is, but it's not a multi-user use case diagram. How does this one user interact with this portion of this system? Good question. The actual bones of what are the classes made up of, those use class diagrams. And this is what we're going to be making in our UML editor this quarter. So we're just describing classes, object-oriented classes. So we're going to have the name of the class, fields, methods, and their associated parameters. And this tells you at a very basic glance, what can this class do? What is its state? What is its behavior? There's no detail on how the methods work, what they do, or even what they return. It's just the name of the method and the parameter list. A question mark would just represent a Boolean, but it doesn't even necessarily have to specify the variable type, although good class diagrams probably specify the type of the variable. We can talk about relationships within class diagrams, because classes are related to each other in an object-oriented sense. Or, yeah, oriented sense. So they can either be completely distinct, or they can have some kind of relation to each other. The different kinds of relationships that exist, we can define association, which just says that there is some association. This could be for instance, a one-to-many relation between a customer and an order. A customer can place multiple orders. A customer can even place 0 orders, potential customer who hasn't ordered anything yet. But this says that these two classes are related. A customer can interact with the order class in order to place an order, or in order to create that order object is associated with a customer who placed that order. Questions so far? Let's talk about the difference between aggregation and composition, something that is very frequently confused in U of L diagrams. So aggregation, one class belongs to a collection. It's either shared, there is no ownership implied within the aggregation, and we have a hollow diamond. A composition also belongs to a collection, which is again why it's frequently confused, but there's a big wall in between. There's no sharing between these objects. There's this concept of a strong has-a relationship. If there's ownership implied by this relationship, then it is composition. If there is no ownership implied by the object, then it is aggregation. So hollow versus filled diamonds are how we're going to refer to that on a diagram. This is how you'll do it on the UML diagram that you create. Let's ask for a couple of examples. So one car has 4 wheels, and one project can have 1 or more consultants. Which of these are aggregation? Which of them are composition? Where is the strong ownership implied?
With the car, because it has to have wheels.
Yes, yeah. Wheels can't belong to multiple cars at the same time, or if they do, I'm a little concerned.
So just to clarify, composition still has like a belonging to the collection. The only distinction is like no shared relation.
Right. Yeah, it's a very strong so a car has 4 wheels, and those 4 wheels belong to that car. They're owned by that car. Whereas a project and a consultant could belong to multiple. I guess a project could have multiple consultants associated with it. There's no there's no ownership implied by the project consultant relationship. How about this class and student and this building and classroom? Which one is aggregation? Which one is composition?
Would student be like a composition or like a sharing? It would be aggregation because it can go between classmates.
Yeah. You can take multiple classes at the same time. You are not owned by this class, and you have the ability to move between classes and take multiple of them. Whereas it is physically impossible for this classroom to belong to multiple buildings at the same time. We cannot physically take this classroom out of the Catalyst building and put it in the building across the street. So yes, this building owns this classroom. This class does not own any of its students. But we'll wait for the first quiz. I'm kidding. What does it look like in code? So let's take a look at, in general, how do objects get constructed with aggregation or with composition? So which one of these is which? Which of these cars owns its engine, and which one is renting its engine, or the engine could belong to multiple cars?
Say composition would be the left side, right?
Yeah.
This final.
Yeah. Yeah, so we're making an engine that cannot be modified. And we're making it in the constructor of this car, so there is no way to pull these two things apart. We don't have to specify which engine does the work. Since the engine is owned by the car, there's only one possible engine that this could be referring to. On the other hand, here, instead of being part of the constructor itself, it's its own setter that sets a passed-in engine as the engine associated with this. You can imagine now that you could now just set a different engine to be this car's engine, and then the old engine is detached from the object. Now, when we go to move, we have to first check if the engine is null, because it's possible for a car to be constructed without an engine. And if the engine does exist, then it can work. Here, a car can't exist without an engine. It's part of its actual construction, so we don't have to make that check. Questions on anything about the application of aggregation and composition? Yeah.
So a big difference is like that engine is final in composition and aggregation is just private.
Yeah, it's final and it's part of the actual construction process. When I put this together, that is built into that process.
Well, these, by the way, yesterday, but all the slides can be online.
Yes, yeah, slides will be posted. You don't have to take notes verbatim. As will recordings. So very frequently confused in practice. Common interview question, difference between composition and aggregation. Generalization. This is just your general word for inheritance. So when we have a superclass subclass relation, it is an open triangle of the superclass. So a button is the superclass of a request button and an emergency button, which are the actual instantiations. You cannot instantiate a button. You would have to instantiate a request button or an emergency button. So we could have a multi-level inheritance system where the superclass is a doctor, subclass is hospital doctor, a general practitioner. This is actually instantiable. Doctor needs further understanding and further definitional work. And cardiologist extends the hospital doctor. Basic stuff from 210 to 11, but the relationship there is generalization. All right, project class diagrams. These are always fun. You can either keep them at their base form, and you can see now that we have some actual composition between these. What is a task? A task is composed of activities. Each of those activities belongs to and is owned by its associated task. Tasks, yeah. Sorry, projects are composed of activities. Activities are composed of tasks. And there's strong ownership implied in this entire direction. So this diagram now shows that here is a composition relationship. And you don't have to ask the question, how do I make this diagram? Now that you know that it's composition, you know when you go to implement it, all right, that should be part of the construction process. I should be embedding this into the constructor as a part of this object that cannot be set later or changed in any way. So knowing about those relationships helps you, the programmer, to be able to implement what a UML diagram specifies. But note that it's designed in such a way that it's also accessible to non-technical members of your team. So you know implementation details from this diagram. They understand how things are related as well in ways that they don't have to understand the technical to understand. It doesn't appear as technical garbage to them. There's something for them to get out of it as well. You can break it down into more. So here are exactly the class diagrams inside of this for what is a project composed of. Well, it's composed of some names that are strings. Description, that's a string. Start date, that is a date object. An activity has fields as well, and a bunch of methods. And this just gives you a sense of, all right, if you needed to implement this, now you have a bit more of a sense of, in general, what you would need to do. Is this enough to go write all of this? Absolutely not. You need much more detailed specifications for how all of these are going to play with each other, what each of these methods actually does, some description for what the boundary is for what needs to be done and what doesn't. So this is not a specification, but it is a high-level diagram of just what needs to be done. How does this system work? Visualized, how does it all work together? We can have object diagrams. So this is what happens when we instantiate our classes. We're no longer dealing with just vague classes that can be instantiated. So what happens when they actually get instantiated in practice? So now we're looking at a structure at a particular time, some time interval. What does it look like? So here's an example of a moment in time. The human resources system development is a project that has a name, has a description, has a start date. There's an activity, there's a task, there are multiple tasks, and you can see how they're all related now as a snapshot in this system. We can talk about sequence diagrams. This just talks about the flow between objects. So refining use cases, dynamic behavior, what happens when these things happen. So let's get a sense of that. We can just quickly look at, for instance, what happens in a particular bank transaction. So somewhere the user clicks a button, what is my current balance, or loads a page that's supposed to display the balance. A request comes in to the bank object with the get balance call with the associated account number for that query. What happens next is the bank will call retrieve account with the account number from the account ledger, which returns to that with the associated account object. Then we need to actually get the balance from that account. So we query for the account, the balance is part of that. So get balance. Now I'm going to go over to the checking account because there may be multiple accounts within that account object. Maybe there's a savings account, a checking account, other accounts, who knows? But now you get the balance from the associated account, return that. Once we have that balance, this returns from whence it came. So it shows kind of the sequence of how objects interrelate in a particular use case. So you can imagine that a large-scale system is made up of many, many, many of these. In fact, each method that is called on a particular object might have such an object or have such a diagram. How does this work? What does it communicate with? This is very important when multiple people are working on multiple different objects. If your task is to build the bank and your teammates' task is to build the account ledger, then you need to know how to communicate something like this, that one person is going to be making this method retrieve account. And this person needs to make sure that given an account number, I return the correct account. There's a little bit of communication that has to happen there because two people are responsible for this transaction. If your communication is not there, who knows if you're creating something that actually works?
These in practice are just getters and setters.
Yeah, trying to keep it as simple as I possibly can for the moment. It'll get more complicated as you go do this in practice. Another example would be communication between a computer and a server sending an email. So the computer runs an automated check email, or maybe the user back in the day clicks refresh my inbox. The first thing that happened when you do that is any unsent mail. This is a very old slide deck. When you did that, it would send all of the unsent mail. So it will then do that, pop up a new email, get a response from the server that says, all right, this is credentialed, etc. Here's your new email. Now we'll download all of that email and delete the old email. So the things that the computer needs to send requests for to the server when the check email button is pressed. There is some sequence of activities that need to happen. This defines visually what they are, who they communicate with, and this way, if you're assigned a particular task based on these diagrams, you know what you need to implement. Not how you need to implement it. There's still going to be communication between you as you implement this, but it at least gives you a sense of what needs to be made and opens the dialogue for, hey, on this diagram, this is there. How do you want to handle this? Another example would be back to our project manager example. The project manager wants to remove a project that is sent to the user interface, maybe the view portion of a model view controller that we'll talk about later. That is sent on to a project class to go find the project. Once we have that associated project, then we find the associated activities. We will find the tasks by the activities, and you can see how this is recursive in nature. We're going to delete all of the tasks inside of each activity, find the next activity, delete all the tasks in that activity until we've deleted all the activities, and then we're done having deleted everything inside of that project. So this visually represents that this needs to be implemented recursively. You can't remove the project until all of its subcomponents are gone. You can't remove an activity until all of its subcomponents are gone. Probably more than we need. Activity diagrams, we can just go through these fairly quickly because these are a little bit less important now. So flow charts are back. How does this actually work? So we begin in an invoice system, a delivery invoice system of receiving an order. Once we receive the order, two things can happen in parallel. We can start filling the order and we can start preparing the invoice. So this shows that actually they can be done in parallel, that we're not waiting necessarily until we hit the join, where once this process is done and this process is done, we can do that. But it shows a bit of a flow associated with this. We can fill the order, then we need to figure out if it's a rush order or a regular order, in which case they're sent off differently to be filled at different times. So a nice flow to, all right, when we receive an order, what happens? Who are we communicating with? How do we move forward? Note also that it's divided nicely between who is responsible. So you can now see that fulfillment only has to look at that side, but now you can see where is it coming from. If I don't have any orders to fill at the moment and I'm sitting waiting for work, who should I talk to? Talk to receive order. Have you received any orders? Is receive order working right now? You can start to debug and plan for future bugs by saying, if the orders are empty, every so often send a request to receive order and just see if I can ping the receive order system. And if that system is down, then alert IT. You can also see that, yeah, it's broken down nicely. The actual delivery component is in its own box in this. So you can easily draw vertical lines for who's responsible for what, boxes around related information. You can see the parallelization that can be done to speed up. All in one nice visual diagram with no words about any of that. It just relies on your own technical ability to read the diagram and see the associated logical connections. I think this is probably mostly good. Yeah, there's your swim lanes. There are also state diagrams. You want to see a lot more of this. They're basically just automata from my own automata and compilers course. So state diagrams just show the state of a particular object and what changes to change the associated state of the object. So here we have a button with two states, either off or on. When we push the button is on. When we release the button is off. Pretty simple, but you can imagine that we have a starting position here for projects not assigned. You assign that resource to a task, increment the number of tasks that are assigned. Once it's assigned, it stays assigned until it's complete, until you unassign. Either resources are idle, which goes back to the resource manager, or we go back to this not assigned state waiting for the next assignment. So state is very useful when there's state embedded in your project. All right, I didn't want to spend a ton of time on this because it's not needed, and the stuff that's following is more important. How are we doing? Questions on anything so far? Before we dive into how to design software, how we've historically done it, kind of what's wrong with how we've historically done it, and what we do in the modern day and why it works. That's where we're headed. The classic version of software development is waterfall. I don't really want to spend a ton of time on waterfall because it's important to understand the steps because we still go through these steps. But historically, how waterfall has been done is that it's all that was done, and that's not okay anymore. So the components of this are very important. Phases, we just go through this sequence of 6 phases, and then the project is complete. How nice. We start by gathering the requirements from the client. So the client comes to us and says, hey, I need a UML editor for my work at this tech company. We really need to be able to visualize the work that we're doing, so we want a state-of-the-art UML editor so that we can explore that. The questions that you might ask during that process, well, great, I need some details. Tell me the details of what you would like me to produce. I need to know a lot more than that, or I'm just going to produce whatever it is that I want to produce, which isn't what you want, which we go back to that comment from yesterday, where I didn't produce what you wanted. We go from requirements. Once we have a good set of requirements from the client, we're going to write a specification document. Everything that needs to be done in order for this project to be complete. What are all of the specifications of this large project? From there, we go into design. Given the specification, how are we going to put this together? What design principles do we want to use? What are the objects? What are the relationships between them? This is where we build the UML for the project. We need to have an understanding now of not just what needs to be done, but how we're actually going to do it. What are the design principles? What are the associated running times of our implementations? Make sure that this is done in this way so that it's not inefficient. These happen at the design phase. We go into implementation, where we take our design, now that we're all agreed on how to do it, and we're going to actually go do it. So we implement, we build it, we build our individual pieces. You build your pieces, I'll build my pieces, and then we integrate them together. So your pieces need to communicate with my pieces need to communicate with your pieces. We will shove them back together and now have a working program that we will then deliver as the product. You can imagine there are some issues with just this by itself, but historically, this is what was taught and done decades ago. But it's still an important process because it is still these stages that we go through. This is still the process that is used. It's just not just like this. Note that testing happens all along the way. We don't wait to test until the very end. We need to be writing tests and making sure that everything is working along all of these stages. So let's go into a little bit more detail. I like how visual these work too. So we're going to be building up a beautiful hexagon. We're going to gather the requirements from the user. What this is going to do in practice is give us a sense of where are the boundaries of what is part of this and what is not part of this. What do you need me to do? What is superfluous? As an example, last year when I taught this course, in the very first sprint, there was a login system that was created for the UML diagram that was not asked for by the user, by one particular group. That is superfluous design that in terms of the gathering requirements was outside the scope of the project. When they went to deliver it to the client, there were some things that should have been in here that were not in here, and they delivered complete stuff that was outside of the scope of what the client wanted at the time. This is a failure at the gather requirements stage, where we need to define what these boundaries are. Do note that the communication with your client is probably not going to be perfect. There will be some misunderstandings. Where is this line? Maybe this wasn't asked or wasn't communicated clearly. But the goal is to understand the best outline that you can, as well as some components of what goes on the inside. You need this feature. I don't know where exactly this goes in here yet, but you need this standalone feature. Great. This standalone feature, this option. That you start to get an understanding of what the internal representation of the hexagon might look like a little bit. So you need to know what it's going to do. Just a raw list of what do you want this to be able to do. Of course, you should be writing this down, taking notes on it. I don't mean in this class, I mean when you're talking to the client. You should be talking to users, clients, customers. They're the ones paying you. So you should be trying to implement what they want. This isn't just what you want to deliver to them. You are working for them to deliver them their vision. You want to make sure that when you deliver it to them, you haven't produced something that they don't want or they don't need. So gathering all the information that you need to be able to plan. Next, specification. This is where we start moving things around a little bit. So we start here, and the goal of a perfect specification diagram is to now specify exactly what the boundaries are and the internal representation is. So this is where we have a complete and total understanding of what we are building. Take those requirements, really hone in on, all right, this is exactly what we need to be making. So written description, what the system does in every single circumstance for every possible input in every possible state. Don't miss anything. This should be a long form written document. Most specification documents are incredibly long and detailed because it covers every possible situation. It is much more comprehensive than the requirement stage. And it is a technical document. So this should be, it should be where all of the technical requirements come out. From the design, this is where we're going to say, all right, we have 6 developers in this team. We need to make a hexagon. We need to divide up the work so that we build this in some nice way. So we are going to divide it in some way that makes sense. Here we have 6 equally sized triangles, 6 equal amounts of work. That's exactly, they should flow perfectly, right? So this is where we define things like the system architecture and how this system is going to be decomposed. This hexagon is going to be built out of triangles. These are what the triangles look like. We're going to make each of these triangles independently. There are 6 of us. This is also where we specify where these module boundaries are and how they're going to communicate. When I make some function that is here and it needs to communicate with something here, what is the interface? How is this going to communicate with that? Because I'm building this and you're building that. We get a lot more now of how the system works because we have to actually figure out how is this going to work together? How is the system actually going to be built up from the ground up? So at the end of design, what we can really do is break apart the hexagon into its individual triangle components. Because the design now says, how are these going to communicate with each other? What is the responsibility of each triangle? What do we need between communication between triangles so that in the end, when we throw this together, we get a hexagon? Note that here we just have the boundaries as well, with well-defined boundaries between triangles. So you could almost throw this slice in between what one group is responsible for and what another group is responsible for. Everyone knows what their tasks are. Every group knows what their tasks are. There's no overlap. Communication was perfect. So boundaries between everything. On to implementation. This is where you take this design of a purple hexagon and you actually go implement it. So our 6 developers go implement from the ground up. And the reason this is a different color is because the design of the specification is in purple. That's what we're supposed to make. And what we actually make is now defined to being in red. And this will make sense in a second. So we code up the design. We have an actual now prototype of the design. We start with the plan. What are the associated order of things? What is the schedule? What relies on some other component? First, we need to make sure that these are implemented so that we can test whether they work, because we're going to be relying on them when we build these components. Assign some kind of priority to each of these. There's going to be a high priority. This is a necessary part of this system. If we don't have it in the first week, we won't be able to build the other components and test them well. So high priority, this needs to be done at an earlier deadline than the entire sprint. Also useful for testing. Every module you make should have tests written for it at this stage, because what you're doing is complicated enough that you need to make sure that it works. You don't want to find annoying bugs way later when they're way harder to figure out where it is. As you're building them each smaller module, that's when it's going to be easiest to debug. It's a smaller system, fewer components. When something goes wrong, way less to look at. You go into integration, we put everything together. And the idea is that everyone coded something a little bit different, each different part of this system. But we now need to go and do a big quality assurance to figure out, does this entire system work together, not just with the individual components? So we should end like this. And you can note that I actually love the way this is put together, because there are little pieces of purple bleeding out of things that we didn't quite get to, or are a little buggy. It doesn't quite work the way that we intended. There's a little bit of an issue with this boundary and this boundary. That's expected. You never produce exactly what you intended to with the specification. The goal is to get it as close as possible so that when you do deploy it, when you do go take it to the client or a user base, then there are the fewest mistakes, the fewest things to fix in the future. So we have a product. And in Waterfall, we just ship, throw a party for ourselves, and wait for the bug reports to come in. So we only have a couple more minutes, and there's one important thing I want to do before we go, which is get one more person a group and then an announcement. But so is everyone sitting with their groups? Is that something that we tried to do when we were in here? So if that is the case, then go ahead and raise your hands if you're in a group of 5 at the moment. So Juliana, you have a choice now of, I guess, maybe huddle together with your group a little bit. So there's a group here, there's a group. Where else?
Yeah.
There's a group there, a group back there. You know any of these people? Have any preference?
Yeah.
Okay, you know what you want to do? Perfect. All right, I think we're good with that then. The other piece of news is that I'm currently working with Jane for people on the wait list. So if you're on the wait list, I plan to let you into the course, even though the cap is 40. I don't care if there are 3 people on the wait list, you'll be in the course. So that is in progress. It's usually easier, but the system was not responding. I don't know if that's been fixed yet, but if not, it should be fixed in the relatively near future. Yes.
Speaking of.
Yes, that's very buggy software.
Straight up out of the system, give me an undefined here.
Excellent. I wanted to make sure we covered that. I think we're probably good for today. we'll come back and talk about what the issues with this system and what we can do about it to make better software. It's Monday, we don't meet tomorrow.
Oh, yeah, no, I'm sorry, the third one. The third. I mean, the one that we're not taking to get. 9 o'clock. Oh. Yeah, they know.